Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video we're going to finish up our second example of wood connection, bolted connection. Okay, so in previous videos we looked at the brace, we looked at the beam, we figured out all of the resistances, the individual resistances for the brace and the beam in parallel to grain and perpendicular to grain directions for the connection, including row shear, net tension, group tear out, and splitting in the case of the beam. We looked at our yielding resistance, and so now we have all of those resistances compiled together, and we can go ahead and check all of them individually to come up with what is the total amount of force, NF, that we can apply to this connection. And we're going to use the overall requirements to come up with that. So those are the requirements from clause 12.4.4.2. The first one is the yielding requirement, which which applies to the entire connection together. So there's not like a separate yielding for the brace side versus the beam side. There's just one yielding check. And so the yielding requirement is that NF has to be less than or equal to NR for yielding, which we calculated was 5.8 kilonewtons. Okay, so this is one requirement on NR, or NF, sorry. So we're trying to figure out what is the maximum NF that we can put on here. So this is already one bound on NF, is that it has to be less than 5.8. So we're not going to get anything better than 5.8 out of this connection, no matter what the other strengths are for the brace or the beam. So now we're going to go through the rest of them separately for the brace versus the beam. So I'm going to start with the brace, which was the most recent checks that we did. So in this, there's only load parallel to grain. So this is also the easier one. So because since there's only load in the parallel to grain direction in the brace, we don't have perpendicular to grain checks to do, which is C, and we don't have the interaction check to do, which is D. So we're only going to check B. Okay, and now the NF is directly in line with the PF. So I can directly, in this case, compare NF, which remember is this one here. So NF here is directly parallel to the grain. So NF and PR I can compare directly. I don't have to account for a component of NF to compare to PR, which is what we're going to have to do for the beam. Okay, so NF has to be less than or equal then to PR. Actually, I think I'll write this as, first of all, that really the requirement's on PF, but PF equals NF, which has to be less than or equal to our resistance, PR. And PR is the minimum of our row shear resistance in the brace, which we calculated as 11.1, our group tear out resistance of the brace, which we calculated as 14.4, and our net tension of the brace, resistance of the brace, which was 44 kilonewtons. And remember, each of these was basically the sum of the resistance of the two brace members, which both resist the load on that side of the connection together. So therefore, our PR is equal to the minimum of these, the lesser, which is this one here. So PR is equal to 11.1 kilonewtons. We anticipate then that we're going to get failure in row shear if we didn't have it in yielding. And therefore, NF has to be less than or equal to PR, which equals 11.1 kilonewtons. So this is our second requirement on NF. And you'll notice that it is not as stringent as the yielding requirement on NF. So for yielding, it had to be less than 5.8. For parallel to grain failure of the brace, it has to be less than 11.1. So our connection will not fail then in the brace. Okay, now we need to check the beam. Okay, so for the beam, our load is applied at a 45-degree angle with respect to the grain. Okay, so we have one component in the parallel direction and one component in the perpendicular direction. So this is our load direction for the bolt in the beam. And so we have a parallel to grain component and a perpendicular to grain component. And this is our theta, which equals 45 degrees. So we can figure out what those parallel and perpendicular components are. And we are going to compare our loads against those components of NF. Okay, so let's do B first, which we've done already before. Okay, so we did it for the brace, parallel to grain. So let's do it again here. So here we're going to have PF equals NF times cos theta. Okay, which has to be less than PR. So the requirement for parallel to grain is that PF is less than PR. How do I calculate PF? PF is going to be NF times cos theta. So it's basically the parallel to grain component of NF. And PR, again, is the minimum of all of those individual resistances. Okay, our row shear, which is 9.1, we did not have any group tear out for the beam because we were not near a loaded end. And our tension resistance was 38, our net tension. So therefore our PR is equal to the minimum of these, which is the row shear, which equals 9.1 kilonewtons. And therefore, if I want to find my NF, I can rearrange that equation above and put the cos on the right side. PR divided by cos theta. Our theta is 45 degrees, as you remember, and then we get 12.9 kilonewtons. So this is our third requirement for NF, which is not as stringent as the parallel to grain one that we had for the brace, which in turn was not as stringent as the requirement for yielding. So still yielding is governing this connection so far. Okay, let's check requirement C now, which is the perpendicular to grain for the brace. Okay, the perpendicular to grain requirement is that QF is less than QR. In this case, our QF is equal to NF sine theta, right? Because now we're looking at the vertical component of NF, and that has to be less than QR. And QR is easy to figure out. There's only one perpendicular to grain failure mode, which is splitting, which we calculated from the beam to be 4.4 kilonewtons. Okay, so that's our splitting failure. And then, if I want to find my requirement for NF, I can rearrange the equation above so that I divide QR by sine of 45, and I get 6.3 kilonewtons. Okay, so that's getting closer to the yielding resistance, but not quite, so that one's still not governing. And then the last one that I need to check, D, is our at an angle to grain resistance, which is an interaction equation. Okay, so in this one, we compare NF directly to this interaction, PRQR, divided by PR sine squared theta plus QR cos squared theta. Okay, and if we do that, we're going to use our PR, which is 9.1. Our QR, which is 4.4. Okay, so I'm using, the actual QR value, not the NF. I was trying to figure out what's the equivalent NF. I have to use the actual QR, the actual PR here. Okay, so those are my resistances in the parallel and perpendicular directions. Then I do PR sine squared 45 plus QR cos squared 45. And what do I get? I get basically 6.0 kilonewton resistance. So it's pretty close to what the yielding was. but the yielding was still a bit lower because it was 5.8. So you see that when I do a combination of parallel and perpendicular to grain, I get a value that is somewhere in between those two. But you'll see that it was less than the value that I got for, what's the equivalent NF if I compare to QR at that angle to grain. Okay, so that's why I have to check both, right? Like this value here, like you would expect, okay, like I take, it's going to be in between 4.4 and 9.1 when I do this interaction. So why wouldn't I just check this one, perpendicular to grain, right? Because this one should be lower, right? But you see that when I account for the angle and I only consider the perpendicular to grain strength, then I get actually a higher value of 6.3 than I do when I compare a combination, in this case, of the perpendicular to grain strength and the parallel to grain strength. Now that might not always be the case, but you can see that sometimes it is the case. So therefore I have to check this D requirement all the time. Okay, so based on all these, I can pick the lowest number of all of these resistances that we've done in this summary, and that gives me the total resistance of the connection. Okay, therefore my maximum NF that I can apply is 5.8 kilonewtons. And we expect that the connection will fail in yielding. Now these two are so close together, 5.8 and 6, that in reality, like if I were to do a test of this connection, could I guarantee that the failure is going to be in yielding? Because that's what this equation says. No, because there is too much uncertainty in the wood strength and in the failure modes overall. Remember, this is a statistical kind of process that we're going through when we're talking about strength of connections. So I couldn't say for sure which one is going to happen, but I can say that 95% of the time my strength is going to be greater than 5.8. That's the idea of the standard. So now I've gone through this whole thing and I figured out my overall strength of the connection. And in the last bolted connection example, we're going to look at how to design a connection from scratch instead of checking one.